Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'm Jim Laris, and it's my great pleasure today to introduce Adam Olander, who is a graduate student at Stanford, near finishing his PhD, he tells me, who's going to talk to us today about some research that he's been doing with Alex Aiken, his advisor, on using influence to understand complex systems. And I have to say, we were talking before this, and I think it's a really interesting technique that we really should try out ourselves. So, Adam.
Thank you for the introduction. As Jim said, I'm going to talk today about using influence to understand complex systems. So we're interested in the problem of production debugging. So I'm going to talk a little bit about what we mean when we talk about production systems and introduce a notion of statistical correlation called influence that we use to address this problem, a system that we built called Chi that computes influence, and then the bulk of the talk will be a bunch of case studies with real systems. So this is sort of our view of a typical system. You have a bunch of inputs and a bunch of outputs. And every now and then you observe some surprising behavior at the output. So that could be an outright crash or a wrong result or poor performance and so on. And inside of the system are all kinds of complex interactions. So you can have loops and cycles, sharing resources, and portions of your system for which you have no instrumentation. So you may not know what's going on in that portion of the system. And indeed, you may not even be aware of all of the components. So if you imagine third-party subsystems may be composed of components about which you know nothing. And the information that you have about this behavior is noisy and incomplete. So there will be likely components from which you have no instrumentation, and the ones from which you do may be in all kinds of different formats. So one might be recording temperature data while another is recording syslogs. And our goal, given that scenario, is to infer the interactions among components in these systems. And we want to do this so that we can build models of behavior, understand how that behavior changes over time, isolate problems. If we have known problems, we might want to understand how those problems relate to one another and rule out potential causes. And so in the case studies, we'll come back to these, and I'll show you examples of all of these. Now, the typical approach for this kind of work is to infer causal dependencies. And what we mean when we say a causal dependency typically is one of two things. Either a functional dependency, that is, one component's behavior is required to be correct for another component to behave correctly, or a communication dependency, meaning that one component simply consumes data from another. And the reason that this is sort of sought after generally is because it's thought to lead naturally to a root cause. So you observe some bad behavior, you say, okay, well, what does this depend on? You sort of move back in the chain, make sure that's okay, move back in the chain, and so on. So you can sort of work your way along the dependency chain, and eventually you'll find some problem, and that's supposed to be the root cause. So that's sort of why this is an appealing idea. And typically we get dependencies either via manual specification. So you tell someone, I want you to write down, basically, what depends on what else. Tell me the topology of your system and so on. Or using some sort of a system modification. So add instrumentation, for example, to record message paths, or turn on debug logging so you get a granularity that's sufficient to know exactly who is causing what behavior. And there's a long list of projects to do this. Some of the more well-known ones, things like PIP and Magpie, Project 5, D3S, Pinpoint, and so on. But there are some problems with this. So the first is this question of what constitutes a dependency. So say you have two components that are using a shared resource. So typically, previous work would say that these two components depend on this resource, but they would not say that these two components depend on each other. But they certainly affect each other's behavior. So this is something that we would like to be able to talk about, but that dependencies don't really handle. There's a question of who maintains it. So if it is a manual specification of dependencies, given that the system is basically going to be a different system every 2 weeks because of upgrades and modifications and so on, who's going to make sure that that is kept up to date? If we do require certain types of instrumentation, how do we get those into the system? what are the overheads associated with getting message paths, for example. And there's sort of a fundamental problem in dealing with discontinuities. So if there's a portion of the system about which you know nothing, dependencies can't leap over this. So you will never be able to say anything about the dependency relationship between this component and this component without knowing what's going on in between. But that's something that we'd like to be able to do. And so we propose this notion called influence. And influence is basically statistically correlated behavior. So we're looking essentially for components that are hiccuping around the same time. And it's an orthogonal notion to dependencies. So you can have two components that influence each other without having a dependency, such as in the resource sharing example. And it captures implicit interactions. So again, if they're competing for a shared resource, you will be affecting each other, influencing each other's behavior, even without having a dependency. It turns out to be a very robust notion, in part because of its sort of statistical grounding. And what we mean by that is that the data can be very noisy and very incomplete. And I'll talk a little bit about that later. And we can also capture time in our analysis. So what I mean is both the, yeah.
Ask, like, is there, maybe just, you can postpone it if you're going to touch on it later. Like, is there a reason to use correlation versus causality versus conditional probability?
Sure.
Dependence?
Sure. So certainly when comparing with causality, it's a question of what data there is to support one or the other. So it's been our experience that you'll have some syslogs being generated on one component and some syslogs being generated on another component. Who's to say whether one is causing the other? There's nothing in the data to support causality, but there's plenty to support correlation, right? So given the data that you have, you may not be able to say anything stronger than that the two things are correlated. If you can't perturb the system, for example, how would you test such a hypothesis? If you don't have message paths, how would you know that one is causing the other?
Okay, so that's kind of one problem, but like statistically you can, just like statistically you can establish correlation, you can establish causality as well, right? There are things that would let you either, confirm or deny a causality hypothesis. And
without perturbing, the best you can do is say that it is statistically very likely that there is causality.
Sure, I see.
Right. But that's essentially what you're doing. So we're not using the word causality because you're not really confirming it if you just have correlation data. But you can say you have a sufficiently strong correlation that you believe there is almost certainly some relationship between these two components. And that's what we're doing. And as far as, for example, using something like a Bayesian network, this conditional probability, that's sort of what this last bullet, this time varying notion. So you can have delayed effects. So one component can do something interesting and a little while later another component does something interesting. And time is not something that those statistical graphical models handle very well.
So is influence a superset of the dependencies?
It's orthogonal. So two things can be dependent and not influence and vice versa.
So there are dependencies that are not captured in influence.
Right, and you'll see examples in both directions later in the talk. From real systems. Okay, so let me go through the sort of mechanics of this a little bit more so you get maybe some more intuition about exactly what we're computing. So at a high level, what we're doing is identifying interesting behavior on individual components, correlating this in time and space, and then summarizing the resulting correlations as a graph. Okay, so let me walk through that. So the behavior of individual components is described by an anomaly signal. So this is a real valued function of surprise over time. So here's an example from a real system. So something interesting was happening around here, and this interesting thing was somehow more interesting than this. And the way we define what constitutes interesting is with some kind of component model. So if you have numerical signals, so throughput measurements and so on, we just use those directly. So the component model is a no-op. If it's something like a system log or some sort of generic common data type, we have standard models that we'll use. So these are just things from the literature. And it's been our experience that doing the easy thing works fine. So do the stupid thing, you're fine. But this is an opportunity, if you do have expert knowledge, to incorporate that. So if you know that a specific sequence or pattern of messages is of particular importance, then you build that into your component model, and that's fine. Okay? But so this is how we're abstracting the individual components in the system. Now, if you talk to administrators of big systems, as we have, this is actually one of their working modes. So they bring up a big screen, and they put a lot of graphs on it, and they know something weird happened maybe around a particular time, but they kind of just need to look at these graphs and see whether they can find something interesting. And so they'll try to look for patterns of, okay, well, it seems like these things all seem to be doing something interesting around that time. Both of those two components, there's some phase change or something like that midway, and this might be a relationship. There's certainly spikes there, but perhaps it's just a coincidence. So the question is, how do we automatically compute and represent these patterns? And we do this using the standard cross-correlation. So I don't know how familiar people are with this, but this is just essentially looking for correlation when you offset the signals by various delays. Okay? So this is a cross-correlation function. This is the delay axis. So what this means is that when we offset these two signals, two anomaly signals, by some amount, whatever this delay is, then they correlate very well. Okay, so you have a peak in the cross-correlation function. And based on the height and location of these peaks, we're going to summarize the cross-correlations as graphs, because this is a pairwise relationship, so this is a natural way to summarize them. So let's say that this is the cross-correlation between two components I and j, they're anomaly signals. If there is a sufficiently strong correlation for some threshold that you do not need to specify a priori or even explicitly, if there's a sufficiently strong correlation, we draw an edge between the two nodes. And if the peak is outside of some noise margin, then we assign a directionality to it. So if within the noise margin, we're essentially saying, as far as we can tell, based on the precision of our measurements, they're happening roughly simultaneously. Okay. And so we call these graphs structure of influence graphs, or SIGs. You can blame me for the name. My advisor doesn't like it. Okay, so SIGs have one vertex per component and edges that are summarizing the cross-correlation. So here's an example of a SIG, which has some components, two fans and a disk, and then this other node, which I drew in a box because it's actually a node that's describing a problem. So it turns out we can describe problems just the way we describe component behavior as anomaly signals, and so they just end up being nodes in our graph, just like anything else. And because it's not a real component, we're drawing it in a box, okay, just to distinguish it graphically. Okay, so the interpretation of this is that adjacent components share an influence. So for example, there's a directed arrow between fan 7 and disk 32. So what that means is that interesting behavior on fan 7 tends to precede interesting behavior on disk 32, but that the two fans seem to be doing something interesting around the same time. Yeah?
So there's a couple questions like, so are you representing disk as like one signal, like in one dimension, or they're like actually you could be getting multiple signals like read latency,
right.
throughput?
Yeah, so for a lot of our systems, you'll have multiple measurements from individual components. And so usually what we'll do is each of those measurement streams will have its own anomaly signal. It'll be its own component. And frequently, there'll be some natural way to summarize them. So we'll often have also an aggregate representation of that disk. So all of its signals is another anomaly signal.
But when you do cross-correlation, you basically take like the K signals of one and the L signals of the other, and then compute it across KL times?
Sure. So just think about any of these signals as being its own component for the purposes of this talk, even if they're being generated by the same physical device. So you would still, if you were interested in the cross-correlation between all of them, then you would compute the cross-correlation between all of them. And you're sort of getting toward this question of, well, that's a lot of cross-correlations, and I'll talk more about that later. All right, so is the interpretation of this, does that make sense? So it turns out there's also meaning from graph structure. So when you have cliques, for example, tends to be, in our experience, indicative of some shared resource. And typically it'll be an uninstrumented component. So we've seen lots of examples where a set of components was in a clique, and it turned out that there was something that they were all using that was not generating instrumentation. And I'll show an example of this later. We did a bunch of controlled simulations to start that I'm not going to talk about today. But the upshot of these simulations was that influence is a robust notion. So it propagates under a wide variety of adverse conditions. So in our experimental setup, you could do things like drop half of the measurements at random, add all sorts of timing and measurement noise and so on. And not only would influence propagate when it was supposed to, meaning there's actually a way for two things to influence each other, but that this method is able to detect it. Okay. So that gave us the confidence to try to apply this to real systems, and so we built a tool called QI to do that. It stands for Querying Influence, and this is another name that Alex doesn't like and you can blame me for. Okay, so the motivation for building this tool was scalability. So the way I've described it so far, you need to compute cross correlations n squared times for a system with n components, order n squared. So that's the main motivation, is how do you deal with this problem? How do you specify which of those pairs you actually want to compute? And then we also wanted to do some associated things like adding and modifying anomaly signals and specifying how you visualize it. So if you think about the computations that you're doing, you're essentially filling out this influence matrix. Okay? So if this is indexed by the component names, and you compute the cross correlation between I and j, then you can fill in two of these entries. Okay, so ij and ji, and each of those entries is going to have the magnitude of this cross correlation and the delay associated with it. Okay. So we wanted some way of saying, well, maybe I only want to fill out some block of this matrix, and so we do that by specifying a focal set. And what this means is I want to compute all of the cross-correlation pairs among members of the focal set. Okay? So shaded in that salmon-y color are the entries we'd be able to fill in if we computed the cross-correlation among all pairs of those 4 components in this focal set. Okay. And we also have a way of specifying a peripheral set. What that means is that for all components in the focal set, I also want to compute the correlation with each of the components in the peripheral set. But I don't yet care how the components in the peripheral set are influencing each other. So that's the pattern of entries you'd sort of be filling in to give you a sense. So you save time by not computing these. And when you have, when there's a big disparity between, for example, the size of the peripheral set and the size of the focal set, this is a huge win. So I'll show this scaling up to systems with many tens of thousands of components. So there are also natural things you might want to express as an administrator that we give tools for doing. So you might want to say something about all the nodes in a rack, describe aggregate behaviors. And so we do this using the time average of their anomaly signals. Okay? And these often correspond to subsystems. So for example, in the supercomputers, the racks, we would build these aggregate behaviors, and we call these metacomponents in the work. Another thing you might want to express is some predicate. So when the log contains this error string. And again, everything is represented as an anomaly signal. And so we have an indicator signal. So it'll be 1 if some predicate's true and 0 otherwise. We sometimes call these binary components. And so if these were the periods where the log contained the error message, then it would be high just around those times. Okay. So this is how we would express when the log contains the string. Another thing you might want to say is there are certain parts of the signal that I don't want you to include in your analysis, so ignore the morning reboot. This is something that I have an explanation for that behavior, so even though it was really strange according to my component model, forget about it. So this will hide parts of the signal, and you can actually use binary components as masks. So you can say, I care about the behavior of node 7 only when it contained the string error. We call these masked components. So these 3 things are a bunch of synthetic components that describe things like aggregate behaviors, let us ask hypothetical questions. If there were a component that behaved as follows, what would that look like in the context of our system? And the ability to manipulate signals. And all of this is just using anomaly signals, either from existing components or using additional information. Okay. So that's this tool. This is QI. The query language identifies pairs to compute, synthesizes components if necessary, and then visualizes the influence as the structure of influence graphs. And we have a parallel implementation of it. This is an example of a query. So I'm going to sort of walk you through the the pieces of this, and I'm going to show you a bunch of examples of these queries on real systems, and so I want to make sure you understand what exactly I'm showing you guys. Okay, so I'm going to work from right to left. So first is the focal set. Okay, so this is a regular expression saying any component that matches, that starts with R3 is going to be in focus, meaning we're going to compute all of the cross-correlation pairs among those components. Perhaps unsurprisingly, the perif equals is specifying the periphery. And so in this case, we have a keyword meta. And what that means is that all of the meta components, meaning these aggregated signals, are going to be in the periphery. So we will compute the cross-correlation between all of the components matching, starting with R3, and all of the meta components, but not among the meta components, not between pairs of meta components. And then this is one of the visualization flags. So what this means is I care about the 5 strongest influences, the top 5. And that's what I want a graph of. 5 strongest influences in my system among all the R3s and between the R3s and the meta components. So this is what that query means. And computationally, this is what we're doing. So we'd be filling out these entries. This is embarrassingly parallel, so it's easy to make faster using more CPUs. So this is number of CPUs and normalized speedup. So this blue line would be linear speedup. And the only reason that we taper off is we're just not feeding it enough data. So the more data you feed it, the closer and closer you get to linear speedup. You just need to work off the overhead of communicating all that information. Okay. All right, so I'm going to start on case studies now, but I just want to spend one slide being clear about what we're assuming about the systems that we're applying these techniques to. So the first is that the components have names, right? And this is just a syntactical requirement for being able to write down a query that says, I want to know about such and such component. They're generating time-stamped measurements. The timestamps are very important. What type of measurement is not as important so long as you have some component model that describes its behavior. So if they're numerical measurements, then you can use them directly as anomaly signals if you like. And for most generic types of data formats like syslogs, we have models that you can use that work fine for us. But if you want, there's an entire field on this subject, the anomaly detection field. So that's rife with other opportunities. Okay, so are there questions before I go into case studies?
What precisely are the inputs? Assume you have a disk, you take the throughput, that is your input, but you have to find the anomalies inside this throughput trace.
So if you have the ability to specify what the anomalies are, then you can use that information. If you don't, then you don't. And you can just use the throughput. So we applied this, for example, to a SQL database cluster. And we just used the throughput measurements directly. So one of the attitude we're going into this with is we don't assume that you can change the instrumentation in the system or perturb the system. So if there's information about, well, what messages are interesting and so on and so forth, then we can use that. And for example, for the supercomputers, we had lists of message patterns that the administrators were maintaining in a little text document on the side that were, I know that this pattern of message is really important. And so we use that to generate binary components, those sort of predicated signals for when those messages were being generated. And so we use that later in the talk to talk about relationships among known problems. So you can incorporate that information if you like, or not. Does that answer your question? All right. So this is the same list of applications for this technique that I had before, but in a bizarrely different order. So this order makes more sense for some reason for the applications. Okay, so I'm going to walk through and I'll tell you about each of these. These are all production systems, and I'll tell you a little bit about the system as we get to the examples that involve them, as opposed to telling you about a bunch of systems that don't mean anything. So first we're going to talk about isolating problems with this technique. So BlueGNL at one point was the world's fastest supercomputer. It has over 131,000 processors. And at one point, it had a problem where full system jobs were crashing. Okay? And full system jobs are really difficult to debug because every component in the system, roughly, is involved in doing that computation. And it turns out that the logs generate hundreds and hundreds of messages around this time. So short of and none of these messages matched any of those known patterns that the administrators were maintaining. So sort of at that point, the only thing they were able to do is to go in manually, right, and just read the logs. Okay, so we want to try to do better, and we will. So we have a clue though, right? We have the rough time of the crash. So what we do is we run the following query. So this last term, which is specifying the focal set, which is actually just going to have one component in it. There are a couple of things going on here. So this is specifying an interval. This is the time that the crash was observed between hour 174 and hour 175. So we're going to build a binary component whose anomaly signal is high exclusively during that interval. And we're going to call it crash. And that's going to be our focal set, that one component. Okay. And in the periphery, we're going to have all the meta components, which in the case of BlueGene was all of the racks. And I just care about the top one. So you run this query, and less than 2 seconds later, for a system with more than 130,000 CPUs, it gives you this answer, right? So the reason it's so fast is sort of twofold. One is that we're using meta components. So these are the aggregate behavior of all of these racks. So for each of these racks, we're doing, many thousands of CPUs, but we only have to do one anomaly signal for it. So the aggregate behavior was actually very helpful here. And we're just computing between the crash and each of those. So we're really only doing, maybe 64 of these. And these are all on, I think, 20 CPUs. So, okay. Yeah, anyway, so what it tells us is that the crash is most strongly correlated with this meta component that is describing the behavior of rack 3. So, okay, that's helpful. And now we're going to recurse. So we're going to ask a follow-up query about the components within rack 3, which looks pretty similar. So again, crash is going to be in focus. In the periphery now are all of the components matching this regular expression, R03. Turns out that in BlueGene, everything was named in this nice syntactical way according to its topology. And so if it matches that, it was in rack 3. We're just going to look at the top 5. And so 5 seconds later, you get this list. And for presentation reasons, I've done some shorthand here. So this gray box with the edge attached to it means that every component within this box has a similar edge attached to it. Okay? And that's just for presentation shorthand. And I've listed them from top to bottom in order of decreasing influence strength. So that guy at the top has the strongest influence with our problem. So out of more than 131,000 instrumented components, this is the one that with 6 seconds of computation time, our method says is the most related to this crashing behavior that we specified by just saying something bad happened around this time. Turns out that around the time of that crash, there were 90 components that generated hundreds of messages. The suspect node, however, generated only 2. And exactly one of those 2 was what's called an alert message. It's a type of message that the administrator wanted to be notified about. And it turns out that it's the only alert message that was generated during that period. Okay, so this was the right component. This was more than likely the component that had caused the crash, and this is the message that the administrator ultimately would have found by their manual search if they had done that. Okay. So I'm going to talk about a very different system, isolating a very different kind of problem. So Stanley was an autonomous vehicle that won the DARPA Grand Challenge. And during the race, it had this really interesting bug where it would, with nothing in front of it, slow down and swerve around this non-existent obstacle. Okay? And it nearly caused them to lose the race, which was a big deal. So they really wanted to understand this swerving behavior. And the only thing that they had, the only clue that they had to go on initially was that most of the swerving behavior was happening between 60 and 100 minutes into the log. It's concentrated near the beginning of the race. This is all that they knew. Well, so we know how to construct this query. We're going to say, well, between 60 and 100 minutes into the log, we're going to make that interval, call it swerve. That's going to be in focus. In the periphery is just going to be all the other components in our system. And in 20 seconds, we get this graph. So what this graph says is that each of the laser components seem to be experiencing anomalies that are followed, or that happen around the same time as this swerving behavior. and that the two pieces of planner software also seem to have this strong influence. And I'll talk about temp in a minute, because it's an interesting case. And the reason, you'll notice that, by the way, this took 20 seconds as opposed to BlueGene, which took more like 2. And that's a result of the granularity of the logging. So we have measurements from Stanley at a rate of about 25 measurements per component per second, whereas BlueGene was generating more like on the order of an hour or so. Yeah?
I actually came late into the talk, so I must apologize. But what I'm curious is, if you get this graph, is it giving you a clue about the nature of the bug, about the reason for the bug?
Right. So I'll show you the follow-up and then talk about how this helped them understand what the nature of the bug was. Okay. The short answer is yes. So if you show them the graph that will be on the next slide, the sort of result of these queries, the Grand Challenge team said that they would have been able to find the bug in about 5 minutes if we had shown it to them. In contrast, it took 2 months, and I'll explain why it took 2 months instead of 5 minutes. So once you have this behavior, you may want to then understand. So these are not grayed because they're in the periphery. So we haven't computed, for example, the relationship between planner info and laser 4 yet, okay, because they were in the periphery. So our follow-up query is going to ask, in turn, how these components are related to each other, the components that are related to the swerving behavior. And we do this using last. So last is just a keyword that says, any node, any component that was in the previously plotted SIG, I want that to be in my focus now. Okay, we're not going to, everything else, all the other flags just get inherited from a previous query. So anyway, you just have to type last. And in about 36 seconds, you get this graph. Okay, so this graph tells you a few things. So the lasers are in a clique together, and this little nugget box is shorthand for saying these are in a clique. And what we see is that anomalies in this clique tend to precede anomalies in the planner software, and anomalies in the planner software tend to precede the swerving behavior. So you show this to the Grand Challenge team, and they understand their system, and so they say, okay, there is exactly one shared component of the lasers. And I have a hypothesis as to why this is happening. Okay? So it turns out basically that there was a shared buffer that the lasers were writing into. The buffer was dropping measurements, and so the laser measurements were stale relative to the other measurements of its environment. And so, for example, you're driving along the road, you hit a bump, you're looking at the ground, but that's okay because you're tilted, and the other measurements from the inertial motion sensor and so on are telling you that you're tilted, so everything's fine. You flatten out, but if your laser sensor measurements don't update, that's what an obstacle looks like, is when you're flat and there's something blocking your sensors. Okay? So it was hallucinating obstacles.
Why was it dropping those? Why was it stale? What was the reason for the staleness of the buffers?
Well, so it was the buffer was dropping measurements. So the way that this was written, the software loop that was gathering these measurements would just take whatever the most recent measurement that it read was. So when the buffer drops data, it doesn't check, so this software loop is not checking for freshness when it grabs the most recent measurement. So it doesn't notice that that hasn't been updated when it was supposed to have been updated. So this buffer was just sort of dropping measurements. And it was sometimes doing it for long periods of time, as long as like a second, which is a lifetime for a system like this. Okay, so the interpretation of this is that a clique implies that there's likely to be some shared component, and the influence flows from there to the swerving behavior. Okay. So this is pointing directly at a likely cause. It's, according to the Grand Challenge team, sufficient to isolate the problem. And the reason it took them 2 months to debug this without a SIG was that the dependencies were actually very misleading. So let me explain why. So if you were writing a tool that was designed to infer dependencies, you would generate, this is the best you could hope for. Okay? So this is a manually generated dependency diagram. It's like the gold standard. This is what the metric you would compare against if you were doing dependency-based techniques. And the reason that it was unhelpful for isolating this bug is that the problem was over here by the vehicle interface, or the manifestation was over here, and the problem was way on the other side by the laser sensors. And the way you use a dependency diagram, as I mentioned before, is you walk backward down the chain from where you noticed a problem until you find something wrong. But it's even worse than that, because the component that's really the problem was the shared component of the lasers. And that's not even on here. So they literally walked backward through this graph and affirmed that everything was behaving according to specification. And so we then showed them the SIG and said, actually, it looks like there's a shared component of the lasers that's likely responsible. And they said, aha. OK, well, so are there questions about this example before I go on?
So you did your analysis before the cause of the bug was known?
So when we started talking with them, they said, we still don't really understand what was going on. We know it had something to do with the lasers, but we don't really have a good explanation for this bug. But even once they knew it was the buffer, they still don't actually have a very good explanation for why the buffer was dropping these things, right? Because that's a third-party component, and I think they just didn't have the ability to go down any further than that. So they don't really understand why this thing was dropping measurements, but the successor to Stanley Jr., the next autonomous vehicle, does not use that buffer. So that was how they solved that bug, right? Yeah.
I'm wondering if there's some kind of assumption in as to why this works around how tightly or loosely coupled these components are. Because one of the advantages of using a dependency graph is versus doing an all pairs correlation or dependency measurement is that you actually manage to cut down on the number of other components you might blame for one particular component. And that turns out to be really useful in certain kinds of settings where there's a lot of tight coupling between components. Because if you didn't do that, then every component would appear correlated or dependent on any other component, in which case, root cause analysis or problem isolation becomes almost impossible.
Right. So yes, there's a way you can incorporate that kind of information. So we think about that as topological information. That's if you don't have message paths and that sort of thing, the dependencies are only going to come for what things are connected to what other things. So that's a topological statement. And so, for example, in BlueGene, we have these rack metacomponents, which are capturing exactly that. I'm saying I believe that things in the same rack are more likely to share these influences than things across racks. And so that's how we capture that sort of a notion. If you tried to do that on Stanley, everything is tightly connected to everything else. So it's clearly unhelpful in this context. In the context of distributed systems, you usually have some hierarchical topology that can help you out. Okay. So there may be problems that you already know about, and you want to understand the relationships between them. So there are certain recurring issues, and you maybe want to know, are these independent of one another, or does there seem to be a relationship? So I'm going to talk about an example from a supercomputer named Liberty. Liberty was the smallest of the supercomputers we worked with, had 512 processors, which is just downright quaint by today's standards. And it had 14 known types of alerts. And this is something that we studied in a couple of previous papers. So I would refer you to those for the alert types. And what we did is we generated these synthetic alert components that I was mentioning earlier. So if say, one of the alert types was error, we would generate one synthetic component for whenever that alert happened anywhere in the system, as well as component-specific alert components. So when node 7 generated this error component, we'll have a separate anomaly signal for that. Okay. So we're just going to ask for the alert components, what are the relationships between them? And this is just to show you an example of one of the other visualization flags. So if you do care about a specific correlation threshold, you can specify it explicitly. So any correlation above 0.1 is going to be in this graph. And so you get something that looks like this. And what it says is that there are some alert categories that seem to be related to one another. But we want to know then, are they actually redundant? So do these three actually provide any information above and beyond any one of them? So we're going to run this last query again. And in the periphery, we're going to look at all of the components that contain this ext. And so what that's going to give us is all of these component-specific alert types. And so what we find is that there are certainly components on which we always see these things together. So node 30, node 156, we seem to basically only see these three all at the same time. But this CCISS error happens on at least 3 components independently of the other 2. So the answer is these 3 are not redundant. This one, at the very least, is providing additional information. And furthermore, we see that on node 176, it seems to be generating these GM these parity errors around the same time. Okay. So this is just a way of looking at the relationships among known problems, which turns out to be something that some administrators are interested in doing. You can also use it to rule out potential causes. So one of the other supercomputers was named Spirit, which is about twice as big as Liberty. And at one point, the administrator noticed some strange behavior on node SN138. Okay, so we want to know, for example, is 138 alone? Is that the only thing that's having this problem? So we run this query, and so in the periphery are all of our sort of non-synthetic anomaly signals, just all the normal components in the system. We're going to look at the top 5, but nothing below 0.25. And in a couple of seconds, it spits out this really simple sig, which says there is one other component, node SN487, that does seem to be related. They share an influence. Okay. Well, so we have a lot of problems we already know about, some known alerts. Do any of them explain this shared influence? Okay, so let's try making a masked component. So we're going to look at the behavior of node 138 when it's not generating this PBS check alert. Okay, so what it's saying is essentially we're going to mask out the portions of the anomaly signal where it was generating this known alert type. So if we do this and then this shared influence goes away, we would know that it was likely related to that behavior because a known problem was happening in the portions of the anomaly signal that were supporting our correlation. Okay. Well, so we mask this out and it doesn't change the graph. Okay, so that was not what we were looking for. That didn't explain the problem. So let's try a different one, a different known alert type. So we could try this CCISS error. So we'll mask that out, and now what we get is a new set of components that share an influence. So 2 things happened here. One is that we recognize that this CCISS error is likely to be related to the shared influence we saw between those 2 nodes. And furthermore, when we mask that, we have now basically revealed additional relationships that were being drowned out by this alert message. So it turns out this alert type is what's called bursty, meaning when it does occur, it makes itself well known. It will generate, I think this is the one that generates hundreds of millions of messages within about like an hour around when it happens. And so when you mask it out, it makes it much easier to see the other things that are going on in the log. And so we both explained what the likely shared influence was, and we were able to now see some additional things that were being drowned out before. Okay. Are other questions on this example? Cool. All right. One of our administrators at a mail server cluster at Stanford did not have any known problems that he was trying to solve at the time. So he was just interested in, can you just build a model of my system? So I don't really have a good understanding of what things are influencing what other things. I just kind of want to understand that. So this was a small cluster, 17 machines. Each of the 17 machines were generating 2 different log formats, a mail log and a sort of spam filtering log. One of the machines actually just generated the mail log. So maybe that was a problem, but he didn't seem concerned about this fact. Okay. So the way we build a model of the system is you just say, I'm interested in everything. I'm going to look at, for reasons of fitting on the slide, the top 47. And in a couple of seconds, you have a model. So cutting a rather long follow-up conversation extremely short, this is useful information. So between this and analysis we did on one of the other systems he was administering, which was a database cluster, there were all kinds of interesting follow-up questions about, well, I'm surprised by this relationship. I would have thought it would have done this other thing. Can you then ask, for example, try to figure out why this relationship is here? Or I would not have expected these to be in a clique together because, half of them are actually in a different building, or, things like this, right? So those are examples of the kinds of surprising interactions that you end up finding. And in the case of the SQL cluster, which I won't have an example about today, it actually ended up helping inform future logging decisions. So in addition to telling him that certain signals were essentially redundant, that they weren't providing any new information above some existing ones, he said it also pointed to some deficits in certain portions of their logging. So there was a particular component that was being implicated by our analysis from which they were not generating enough data to ask any further follow-up questions. Sort of brought it down to as far as they could go, and they said, I really should be logging this additional information. Okay. So it turns out sometimes, even if you don't have a specific question you're trying to answer, this can be a good way to generate those types of questions.
So how do you find redundancy from graph?
So in the case of the SQL database, you had lots of measurements like bandwidth, interrupts, and all those sort of standard metrics. And what our analysis is doing, like if you have, for example, two of these metrics that are correlated, with like 0.99 or something like this, which sometimes was the case. They were essentially identical. Like when one was varying by, twice as far as it normally goes from the mean, the other one was doing the same thing, and you basically are not getting any additional information from this. And then it's just a question of which one is cheaper to measure. Sometimes, though, most often, that's not so clear-cut, right? So what it'll say is there's a lot of overlap between two signals. But then the interesting question is, where is there not overlap? So when is one of them providing you with information that the other one doesn't? And so that's something that you can get out of our analysis, but not through this interface, not through like a graph. And this is, I don't want to make it seem like the graph is sort of the most important aspect of this analysis. So it's really about the cross-correlations and understanding the delays of influence and that sort of thing. This is just a particular visualization that we found to be useful. Okay. Another nice thing about structure of influence graphs over typical dependency graphs is that they capture the fact that systems are changing even when they're not being modified, the relationships among these components and the way that they're influencing each other. And so I'm going to talk about an example from a vehicle named Junior, which is Stanley's successor. And Junior wasn't modified at all during the race. But if you look at portions of the race and how components were influencing each other, it turns out that changes over time. So this is Junior's dependency graph, which is static. But if you look at his structure of influence graph, this is the difference between the second third of the race and the last third of the race. So the dashed lines are influences, that disappeared between the second and third legs. The, I guess, slightly thicker arrows, which are like here and here, are edges that appeared. The open-ended arrows are ones where there was a directionality that we didn't observe before, and so on. And I promised you that I would explain the temperature sensor in Stanley, and that's actually relevant to this dynamic nature. So let me just go back to that quickly. So on Stanley, we had this interesting temperature sensor, which has a directed arrow to the swerving behavior. So it seemed that surprising behavior in the temperature sensor was preceding surprising behavior in swerve. So it turns out that it's actually anti-correlated. So what that means is that the more anomalous the temperature sensor became, the less swerving behavior we observed. Okay? So why would that be? Well, it turns out that the swerving behavior only happened near the beginning of the race. So this is out in the Nevada desert, and they started basically at sunrise. So it was very dark and cool at the beginning of the race. And over the course of the race, the temperature sensor heated up. And it turns out that in addition to reporting higher temperatures, the times at which it reports those temperatures becomes more erratic. And as a result, the anomaly signal increases. So you can actually, the temperature sensor, the measurements it's generating, it's like a timestamp, temperature, timestamp, temperature, timestamp, temperature. You strip out the temperature and just look at the inter-arrival times, you can actually tell what temperature it is. Because the inter-arrival times become more erratic, and they become more erratic so predictably that you can tell what the temperature is without looking at the content of the messages from the sensor. But at any rate, over the course of the day, because it's out in the desert, it's getting hotter and hotter, this is getting more and more erratic, the anomaly signal is steadily increasing. Whereas the swerving behavior was only happening around here. So they were anti-correlated. And you get this spurious influence. Okay? So this is an example of something that is strictly dynamic.
Actually,
Yeah.
I'm curious about this. So in your experience, how many such examples of spurious edges did your analysis generate? I think it's hard to determine that without knowing a heck of a lot about the system being analyzed, right?
Right. So at the end of the day, for a lot of these, we don't have a ground truth to work for. So we have lots of examples of we showed them this influence and it matched with something, or it surprised them, but then we were able to corroborate it, like we were able to explain it after the fact. We have almost no examples, other than the temperature sensor, of showing them a correlation and then finding an explanation that said, that was a mistake. We just don't have a lot of examples of those, which is unfortunately not the same as saying we have lots of ground truth and we almost never get it wrong. But we just don't have that data.
I have one more question about your method for generating these influence graphs.
Right.
So I imagine that you are basically processing the log and left to right, I suppose, beginning of time to end of time, and then generating these graphs?
So we have two. So the one I'm talking about here, yes. We also have an online implementation.
I see. So what that means is that you can basically keep updating the influence graph as you process more and more of the log.
Right.
I see.
So that's something that we can do as of like 2 weeks ago.
Okay.
So I'm not talking about it today, but we do have a streaming implementation, which is pretty fast. We use some online principal component analysis and lag correlation techniques, basically pipeline them together, and it turns out that you can use this to get the same kind of information online. So you could, if you wanted to, just kind of have some small graph in the corner and just like watching it change over time. That hasn't been a use case that's come up for our administrators. They seem to be either interested in answering a particular question in a sort of query mechanism way, or they just want to see a picture of their system to generate those questions. Which is not to say that if we gave them a tool like you're describing that they wouldn't find use for it.
So there's a problem, right? If the graph actually changes without any explicit external change that you can see, then what time window to compute things over?
By which time window you mean what portions of the log should you look at? Right. So it's a really important question, and there's no good answer for it. I mean, the fact is your system's behavior is changing over time. Right. So the question of how do you know which portions of the log are interesting? In the online work that we've been doing, we've been looking at trying to identify what we call phases of the system. So remember when I showed all of those anomaly signals at once, and two of the ones I circled, the anomaly signals were doing something, and then they both seemed to suddenly start doing something different. So one of the things we were trying to do with this online tool is identify those phases automatically. And then the answer to your question is you chop up the log into those phases and look at those separately. So in the meantime, you look at all the data that you have.
So do you know when you don't have enough data to either say there's a correlation or there's a lack of it?
As in, do you know when to say,
don't know.
I don't have confidence in this correlation even though there is one?
Versus having a default programmed in that says, okay, there's a correlation and there's not a correlation. Like, do you give?
Yeah, so we haven't done that. You can. So in our systems, even when you have no measurements, we don't treat that as a lack of information. We treat that as signal. So when a component is normally generating some messages and then suddenly stops generating those messages, we don't treat that as an I don't know, which statistically would reduce your confidence in the correlation. We instead treat that as that's really interesting. You normally generate messages.
Right, so what exactly happens so this is a very low level question. So let's say you have throughput measurements and then they disappear. So how does the cross correlation treat this disappearance as?
So depending on the context, you can generate hyatons, for instance, which are essentially a separate kind of message that says nothing was generated during this period. And the algorithms that we're using in this work for the system logs, so not for Junior, but for like the supercomputers and the clusters, would just treat that as any other kind of message term. And so if those hyetons are really common, then it would result in a pretty low anomaly signal. If it were almost never the case that this component were silent, then that hyeton would actually be really an interesting signal, and so you'd get a spike in the anomaly signal. So it just treats it as any other term in the log. You could certainly do something more interesting with that, but we haven't. So just to summarize the case studies briefly, these were all, again, real unmodified production systems. We had no input in terms of what information was being logged. We couldn't perturb them to test these for causality or anything like that. We used generic component models, so these were just bag of words style things for the syslogs and timestamp interarrival times for the embedded systems. So nothing clever in the component models really at all. But we still were able to find tough bugs, reveal interesting interactions, and the admins have universally found this to be useful, both for solving problems and for understanding their systems better, generating new questions to ask. And it's fast enough to be used in an interactive way. And as I mentioned, we actually have a streaming implementation now. And so for all the systems I've talked about, even just on a single core, the streaming implementation is fast enough to keep up with the rate at which data is being generated, which is not to say that there are not systems that will generate data too quickly, but we have ways of dealing with that too. And the one thing we're working on is, again, this automatic detection of phases, as you brought up before. So we'd really like to understand when the system has changed significantly enough that we would like to be made aware of it. And again, sometimes that'll be because you upgrade software. Sometimes it just got hot, right? Okay, so in this talk, I proposed a computing influence, which is the statistical notion of correlated behavior for understanding the interactions of components in a production system. We implemented a tool called Chi, which lets you run queries about that kind of influence, applied it to a bunch of real systems, and hopefully I demonstrated to you the value of this kind of notion, especially in contexts where computing dependencies is not something that you can do with the available data. Okay. And we would really like more examples of finding live problems in active production systems that could either not be detected or couldn't be diagnosed by other means. So there's my ulterior motive. So if any of you have interesting data sets that you think we could look at or that you could apply our tool to, I'd love to talk to you. And I'm free for a couple of hours this afternoon. So that's it. I'm ready to take questions if there are any left. Yeah.
These static dependency graphs, the nodes in them, are they the same as the nodes in your influence graphs?
For Stanley and Junior, there are nodes in the dependency diagram that don't appear in the influence diagram because the components did not generate any measurements. So, for example, file system is something in Junior's dependency diagram, but there was no instrumentation collected from the file system. But the converse is true. So any component that is in our influence graphs is here. But there was, for example, this shared component of the lasers that our technique essentially inferred the existence of that didn't generate data, but was effectively implied by our influence graph, but is not anywhere in the dependency graph.
So your technique can actually infer nodes somehow?
Well, so when you see cliques, it's been our experience that it's very likely that there's some shared resource, and often that corresponds to an uninstrumented component. That's been our experience. It's not required that that be true, but it turns out to be really useful. So I mean, it helped diagnose the Stanley bug. So, yeah.
Has anyone thought about applying this to the economy?
I mean, yes, but people have thought about it. So in addition to the economy, I met a professor, Harvey Miller, I think, at the University of Utah, he's a computational geographer. And so he had traffic data from the state of Utah. And so one interesting question is, can a traffic jam on one side of the town cause a traffic jam on the other side of town without causing one in between? So you kind of nod your head and you say, okay, I could see how that could happen. And the way that that happens is you have a covert channel from which you have no instrumentation, which is the traffic report on the radio that tells people there's a traffic jam over here, so everyone take this other road, and then you have another traffic jam. And I also talked with a gentleman who I think, at the risk of maligning his affiliation, I think he worked at Ford and was actually doing computational neuroscience. Now, why he was at a car company doing that, I couldn't tell you. But he said that the way we interpret MRIs and other measurements of brain activity right now, you are kind of looking for spikes that happen around the same time. You know, show people pictures of mountains and then pictures of faces and see which things light up and whether there's an order in which they light up. But this notion of having an anomaly signal underlying that to filter out what behaviors are already well understood before applying those other things, he says, is not something that they do. So we see a lot of applications for this kind of technique because complex systems from which you don't have very good instrumentation and measurements, those are really common. So it's really easy to find systems to which you can apply it. We just need to collect data.
Yeah. Go back to like correlation versus causality or conditional probability.
Yeah.
In your examples, like how often like directionality actually help you? Like it seems like correlation, unless so you're getting directionality of some sort based on time lag of logging, and those time lags are present in some systems and not in others, depending on how small the scale of the system is and things like that. So in your case studies, like I'm trying to see would having more directionality help you, or directionality that was there was not really, you were doing just fine without having any sense of which way the influence is flowing?
So in the case of Stanley's bug, for instance, the directionality was very important. So it could have just as easily been that the planner software was misbehaving and causing backup upstream to the sensors. That was an equally sort of plausible explanation without that directionality. But it was pretty clear that there was this delay between when interesting stuff was happening at the lasers before it happened at the planner software. So in that case, the directionality was very helpful. In the case of the supercomputers, the granularity of our instrumentation in terms of time was such that we didn't find a lot of interesting delays. The clusters, we found interesting delays again because we had minute granularity. And it turns out that there are things that happen really slowly. So we found a neat bug in one of the SQL database clusters where you would have a spike in a couple of metrics followed by a gradual increase over about 3 hours of slow queries to the database. And eventually that would cross some threshold and you'd sort of collapse and have to reboot the thing. And so this is a really hard bug, right? The proximal cause is pretty far away temporally from where you were actually observing bad behavior. And so this helped the administrator understand what was going on, right? So we were able to say there's a delay of like 3 hours between when we see this and when we see this. And so our tool doesn't report very many of those. And so you can sort of just look at them and say, oh, that makes sense or that doesn't make sense and so on. So we found delay to be really useful. And in the absence of a way of testing causality, that's the best indication of whether one thing is likely to be causing the other. It's the directionality on the edges.
So why can't you do causality in the sense like it's like, there's a statistical formula for computing causality.
Well,
you just look at
it's a statistical formula for making the leap logically from it being correlated to it being causal. There is nothing that says that it is definitely causal. It can be very likely to be causal.
Sure.
And really all that is the correlation sufficiently strong. So in the case of these systems, you have so what that formula is telling you is, do you have enough supporting evidence, right? Based on the null hypothesis, right? Do you have enough supporting evidence to accept instead that it's likely to be causal? In these systems, you have the same number of measurements from all of the components. So the stronger the correlation, the more likely it is to be a causal relationship, either between the two or with some third component that you're not looking at.
Right.
That's the only unconstrained variable is the correlation. If you did that that analysis of is it likely to be causal. It's the only other variable.
So your influence is just based on correlation, right?
That's right.
So what is it? I mean, it's the same as, I mean, causal is just an English word.
No,
You have to
it's-
define it, right?
Well, it gives you a direction of influence as well. Rather than just telling you these two influence each other, it will tell you, if there's data, it will tell you which way the influence is flowing.
But he has these arrows. Why
Well,
are
those are based on time. So if there was no time lag, then you wouldn't be able to tell which way the influence is flowing.
Right. So in a
Oh, I
typical
see.
dependency diagram, the arrow means who depends on whom, as opposed to what happens before what, which is what our arrows mean. And what was your name, by the way?
Ratul?
Ratul?
Yeah.
So what Ratul was suggesting is that even if you had an undirected arrow, meaning things were happening basically simultaneously, it might be helpful if you could establish causality, that this is doing something interesting, and then because of that, immediately afterward,
how
something
would
else.
you do that? So he's using the parameter time lag. You have to use some other parameter, foo bar bad, right? What parameter would you use?
No, you just take same signals and then like the way you kind of measure causality is like look at if this event happens with what probability this happens, and then in the absence of this event what happens. So you try to establish.
But so the idea there is that you have discrete events. And so we're using anomaly signals these are real valued signals so that we can retain as much information as possible. But in the process of retaining as much information as possible, we're getting as far away from categorical data as we kind of can. So the traditional, like, trying to make a Bayesian network would be sort of arbitrary from this. We'd be just chopping up our measurement space.
So in the interest of kind of full disclosure, we did a system last year at SICOM which was just looking at like small enterprise networks, and we found there was no time lag in that particular. So this is like a small enterprise network with computers and things like that. So time lag was not a good indicator because once something failed, it just spread. This is a small network; it will just spread immediately to other components in the network. And you're right. I think we found causality really hard to compute because of lack of data. There wasn't enough statistical evidence for data. So what we ended up, but we found correlation would end up merging everything together, that everything depends on everything, again, because a small network really tightly coupled with each other. We found conditional probability to be useful, in the sense like, take the statistical formula for conditional probability, which is actually, you're right, it's meant for categorical data. But the thing about these signals that are real valued is that small perturbations can be meaningful in the sense like, when a system says 3 and a system says 3.5, they're actually close in terms of what the system's doing. You can actually use that to compute some extension of conditional probability by assuming 3 and 3.5 are close to each other and things like that. It's not exactly discretization of data, but it brings in like
You sort of fuzz
behavior
it,
of systems.
essentially.
Yeah, it's kind of like
Sort of
extension of.
Proximity-based categorical fuzzing or something like that.
It's
Like,
it's
if I see this and this,
Yeah.
then I put a tick in this box and half a tick in the
Yeah.
boxes around it or something like that. Right?
I'll send you a pointer.
Okay.
So it's something.
But when you asked about using topology to reduce your search space, I should have guessed that you were a networking person. No, seriously, when I gave this talk at AT&T, actually, I ended up having that same conversation with a group of networking people. And they said exactly what you're saying, which is that topology is sort of the only way that they can constrain the search space to something that's manageable, and that if you just use correlation, you just get a billion correlations and you just don't know what to do with it.
So my setting was a little bit different. I am a networking person, but it was, the components in my setting were like individual processes on a machine.
I see,
And-
okay.
And we found dependency graphs like no matter like really useful, because otherwise, if a machine's overloaded, all the processes are gonna appear funky.
Right.
And if you did not have a dependency graph in that setting, you will essentially, if you've got 100 processes, you essentially have like, 10,000 high correlation edges in your system and whatnot.
Right.
So
So
trying to
what
just
happens
make-
if you mask out the periods when you have high traffic?
But that's the period you're trying to debug, for instance. So just masking out time does not help. For instance, if you want to debug your servers running slowly, what do you do? Like, if you just compute simple correlations in that particular setting, everything just appears dependent on everything because there's just too much changing in the network at the same time.
Okay. Right. Well, at some point you have to say there may not be support in the data to answer the question.
So I kind of like this. I think the thing I find somewhat missing in my own work and other PCs I see on diagnostics and stuff is there are kind of like a wealth of techniques out there, and there's a lack of understanding of like when a particular technique works in what particular setting. Like the kinds of techniques we did and I'm describing, I wouldn't be able to characterize when it works, when it does not. All I know is it works in the setting we tried it on, and I'm guessing this kind of applies to what you're doing, and there's some other works as well, and that particular piece I find like that's why everybody when they look at different domains they end up kind of inventing their own diagnostic.
So would all
right, so this is a nice hammer, but how do I tell if I have a nail?
Or what nails does it actually?
Right.
Yeah.
So by the way, or do all these things fall under the rubric of machine learning?
I guess. I don't know what doesn't fall under the rubric of machine learning. Any stateful program seems to me like you could call it machine learning if you like. It doesn't use some of the standard machine learning type techniques, at least in this context. Our streaming one uses principal component analysis, which I feel like, sure, I guess that's a machine learning technique. I mean, it's just applied statistics, right?
All right, we should go.
Not to slander an entire community on camera.
Do you want to join us for lunch?
Sure. Where you guys want to go?
Wherever you want to go, yeah.
No pressure though.